Okay, so today we're going to have a look at a theory called Thales Theorem. Now, I'm going to go through this in a minute, but there's a bit of background knowledge that you need to have before you can progress to try and solve what Thales Theorem is all about. So first of all, you need to know about types of triangles. So we've got a triangle here, which might look familiar. And then we've got a triangle here, also might look familiar. And then we've got a triangle here that might look familiar. Now you might want to know what kinds of triangles these are. You may already know. So first of all, this one here, that's a right angled triangle. That's very important to know for Thales theorem. Another one here, this one here is scalene triangle. So let's just write them up on here. It's a scalene triangle. Now we know this because all three sides and all three angles are different. Now the right angled triangle, which is here, this is also a type of scalene triangle because all three sides of this are different as well. And then the last one here, which is going to be very important for us as well when looking at Thales theorem, is an isosceles triangle. So an isosceles triangle, you might want to remember that this one has two sides that are completely equal. They're exactly the same, which then gives us these two angles here, which are equal as well. So that's the first thing about triangles. Now we need to learn something about circles. So if I just try and draw a circle here, which doesn't look too much like a flat tire. Now we draw a line that intersects the circumference at two different points. This line here, this is called a chord. Okay, so now if you've got something which is called a inscribed circle, we've then got two chords which that one endpoint meets. So we've got this endpoint here which we could call A, this one we could call B, then we could draw another chord anywhere. So I'm going to draw one here. So this one here could be the point C. So that would be inscribed in a circle. That just means two chords which are connected. Okay, so now what about if we have three chords connected inside a circle? So let's draw another one. So here's another circle. Got a chord here. We can have another chord here, and then another line here, which is also a chord. Now these are three chords which are inscribed in a circle. Now in this one, our centre point here does not connect any part of this triangle. So that's not quite what we're looking for when we're looking for Thales theorem. So the circle we're looking for and the triangle we're looking for is when one of the chords intersects the centre point. Now you know what that is. That's going to be the diameter. So this is the circle, which is the main focus of what we're looking at. So that's our centre point. We now draw any diameter. So I'm going to draw this one. So let's assume that's a straight line. And then what we do now is draw two more chords. So the diameter is also a chord. So we pick a point. Let's put the point there. And then make two more chords using that point. So connecting this side of the diameter, and then we'll connect this side of the diameter. Now what Thales theorem is interested in is what the value of this angle here is. So I'm going to call that angle X. Now if we did the same on this circle, for example, let's assume that was the centre point. We can also draw another one there, and then our point that we'd be interested in terms of Thales theorem would be that angle there, which we could call point X. Now the easiest thing to do, perhaps get a protractor, try and measure it, but that's not going to be very accurate. So we need some sort of concrete evidence as to what we're going to do to find this angle. So usually when you get a geometry question and there's no values or not many values given, best thing to do is start by drawing lines that you're confident and you know what they are. So if I just draw this circle again, let's draw it over here. Let's try and reproduce that. So we got our centre point, draw our diameter, which is slightly leaning, and our angle here, which we will just call angle T. So put the centre point there, a point there, call that T, and now I'm going to draw my two chords which connect with the diameter. Now we want some proof that we know what the angle is going to be all the time. So first thing to do is we can have a look here at the lines we know, and we know how to calculate them. So this one here is a diameter, these two are chords. But one thing we could do is, we know that half of the diameter is the radius. So half of the diameter equals the radius. So we can draw another radius inside this triangle here, inside this circle, and we could just create another radius. So if we go from here to here, that's going to create a radius. So let's just do that. Okay, so now we're trying to solve this angle X for this triangle, and now all we've done is create two more triangles. So that's made the question look even more difficult. But if we look inside here a little bit more closely, we've now got three radiuses, so three radii. So we've got one here, we've got one here, and we've got one here. So these three sides are all equal. So we could put a line here, a line here, and a line here to denote that those three are all equal. Okay, well that's all well and good, but what does that mean? Well, it means we've now got an isosceles triangle here and an isosceles triangle here. So we've got this one and we've got this one. So I'll just disconnect it a little bit, just as if I'm breaking it apart. So now we've got this one and this one, this one and this one. So we can flip them around and put that on the bottom. And that's how we normally draw our isosceles triangles, but this is still valid. So therefore we can say that also this angle and this angle is equal, and this angle and this angle is equal. So we could give these a name and then try and work out what we've got. So we could call this angle J, so they are equal, and these two angles we could perhaps call them angle K, because one thing is for certain, although the sides are the same, the angles J and K are probably not the same. So we could say that J does not equal K, as in terms of the angles. Right, okay, so where does that leave us? Well, let's fill in this triangle here, just taking that diameter out slightly, just working out on the main triangle. So that's this main triangle. And then what we can do is use this intersect line here for this other triangle, this one, and fill in the names of the angles. So we've got angle J and angle J. And then these two will be angles K. So we've got K and K here. So let's just put our usual line that we like around them to show that there are angles. Now one thing we know is how many degrees is there inside a triangle. So a triangle equals 180 degrees. So we know if we add all these up, we will get 180 degrees. So let's just write that down in some sort of equation. So one there, that's angle J. Got this one here, which is K. And then the final angle is J plus K. So I'm just going to circle that into some brackets. So enter that into some brackets and say that's 180 degrees. Well, we can simplify this up. We've gone through this before and have to simplify an equation. We've got J plus K plus J plus K. So the brackets, we can just remove that. And we can write J plus K plus J plus K equals 180 degrees. That's not changed our equality of the equation at all. Now we can put like terms together. So now we've got 2J plus 2K equals 180 degrees. So that's working well. Now we can factor out a 2. 2J plus K equals 180, still in degrees. Right, okay. Now what we can do now is divide both sides by 2. So carrying on over here, if we divide by 2 and then divide this side by 2, we can write J plus K equals 90. So that's what we can derive from using those calculations. And now we've shown a proof of Thales theorem, which will show that this angle here, J plus K, which is our angle X, so here X equals 90 degrees. Now wherever we draw our triangle, our angle X is always going to be 90 degrees. So if I draw another example here, take my diameter, let's say we go here, and I put my connecting point even this far down, and then I draw a nice line down to here, and another one here. Again, this angle here, that one is going to be a right angle, it's going to be 90 degrees. So instead of me telling you how to make the formula, here you've proved that the formula is actually as it is. So it's a real thing for Thales theorem. So Thales theorem says that a triangle inscribed inside a circle with one of the sides going through the centre point, the angle opposite the centre point that meets the two chords that are not connected to this long side, that is always going to be a right angle. So this X, we can rewrite it and say wherever we draw it, that X will be a right angle.